Hello, and also a warm welcome from my side. My name is Alexander Fischer, and I'm a co-founder and product manager at SimScale. And I want to show you today how you can do a thermal optimization of a cooling plate for an EV battery pack, and how you can do so simply via the browser. So the agenda for today foresees that I quickly introduce SimScale as a cloud-based simulation company, and that I talk a little bit about how we empower engineers across organizations and teams to use simulation really as a daily tool. I will show you then in our case study how this can be applied to a real world scenario where we will look at 3 different use cases: a programmatic cold plate study, a thermal design validation, and an iterative design update. Afterwards, I will show you this in a little live demo on the platform, and then we will move to the Q&A. The session is rather short, so I will try to not dive into any details, but I would be really happy to answer any questions, even if they are detailed around this later on. So SimScale was founded around 10 years ago, and meanwhile has offices in Munich and the US, but we have employees across the globe essentially, which helps us also support customers from all countries and all regions. And we have really many users that are using SimScale worldwide, partly paying customers, partly academic users, and community users that contribute to the simulations as well. We try to really empower engineers, as I've mentioned, based on the architecture and the differentiators that we provide as a cloud-based tool that offers a lot of flexibility and scalability by design. So we call ourselves a cloud-native simulation platform. Essentially, what this means is, for you to make use of simulation and access the service, all you need is a stable internet connection and a standard web browser. That's all you need. You can log on and start simulating right away. We have one platform where you can do various physics. So there's a broad application spectrum that you can use, and it's really for all users. That's also how our user interface is designed. So you can use it if you're a beginner and use all of our default settings and the data that we provide, but you can also go really into detail and use it as an expert user. And more importantly, if you have both of these types of users in your organization, they can also very well collaborate. So that's what the architecture by itself provides. So you can share projects. The experts can really help input and output wise with simulations. So they can share simulation templates in the user interface. They can share scripts for the employees, but they can also take a look simply at the simulation results and offer help. And if that's not enough, we obviously use the same tools. So you can reach out to SimScale via simple chat functionality live while you're working on the platform. And then somebody can help you jump on your project if you share your application with us. It also works on any scale. So you can do small, bigger simulation, computational heavy or not. So you can run, for example, on 4 cores if it's just a small problem, but you can also scale this up to 96 cores. And even more importantly, there's really no limit for you of how many simulations in parallel you want to do. So if you want to be fast, if you want to compare designs and make calls based on data, that's perfect for you, because the computer will be working for you while you save a lot of time. And it's quite cost efficient. There is some licensing model around it, but essentially you're paying mostly for the usage that you have on the platform. So kind of every time you simulate, we will have some core hours that you're using, but essentially it's limited to what you really need. There's different use cases now for such a platform. They range from very few simulations to a lot of simulations. So if you want to name them, that's, for example, in the simplest case, a design validation. So you have just one model. You want to understand if your design is good enough, if it meets your requirements and objectives. And if that's the case, you're good. So you just need to run it once, or maybe you run multiple different versions, but that's it. If you're not happy with the design that you come up with, you might start an iterative design study. So you might look into the results. You want to see essentially what can I improve, and then come up with a new design, replace it, run a new simulation. Likely you will do a few iterations of this, so you're probably around 5 to 10 simulations or in that range. So you can still do this in the graphical user interface, but you're already making use of more simulation. If you want to go further, though, if you want to really start simulations with many parameters, etc., you might reach hundreds or thousands of simulations. And then even with an easy way to replace or update your model, that's not the most efficient for you. So you likely want to use then an API, so a programmatic interface, and script what you're doing. These might be also different use cases, like, for example, design automation, generative design, or design optimization. And you could also go further and integrate your workflows into a bigger scope. So you might couple your 3D simulation with 1D simulation models, or you really want to integrate the simulation workflow into a digital twin operations model if you want to. So these are the different ways how you can do simulation. And in our live demo today, we want to look at this very simple case of a design validation, but also how we can move this into an iterative design study, and all of this based on a design optimization that we do via the API. So this is our case study. We have a EV battery pack, and we start with a cold plate that is used for cooling the battery cells in the pack. So we start with our geometric parametric study. We have an aluminum cold plate with different parameters that we want to change. So we have 3 base designs that have different flow channel ducts, but we also want to add some turbulence elements in here. So simple cylindrical parts in our case, where we have different distribution patterns, so more or less, and we have a different diameter for these elements. That gives us in total 12 different cooling channel designs that we want to simulate and start via API. From this, you can potentially already see that we are simulation experts. We really leave then the best designs up to you, but I think it will really give you a good indication of how it can help you make these calls and iterate efficiently over different ideas. The main design objectives are probably quite clear. We want to have efficient cooling and ideally uniform cooling, and we want to have that at an acceptable pressure drop. So we likely need to do a trade-off here for the best fit for our application. And we will do this via simulating the physics of convective flow. So we will only have the flow channel of our cooling plate, and we will run an analysis where we take also the thermal aspects into account. We will do so right in the beginning. You can see here now the different designs. And as this takes some time to upload the geometries, mesh it, and simulate, we will start with this. But while the script will be running, we will look at a design validation as well. So we will take the full pack. We now see one of these design variations that we have for the cooling plate. We will mount this on top of our battery pack, around 400 cells. Where we have now our liquid cooling plate, trying to reach the objectives of a suitable operating temperature and a ideally uniform temperature distribution that we want to keep below 5 degrees C or Kelvin. The physics we're going to simulate is conjugate heat transfer, so essentially taking into account all mechanisms of heat transfer. In our case, mostly convective and conduction is interesting here, but we could, of course, add thermal radiation as well if we want. Good. And as a second step, we want to go into an iterative design study. So essentially, if we got out of our more simple model or reduced model of the cooling plate, a good indication of which of our design variations should be working best, we can also validate this again by just replacing the cold plate in the full assembly and just kick off another run. So that's what I will also show you later on. Great. So let's jump into the live demo at this point. So what I will be doing here is I will simply open up now a new tab. So I'm here in a standard web browser. And to start a simulation with SimScale, what I will be doing is simply typing here simulation new and enter. this brings me now to my dashboard. I can open up here now a new project. If I wouldn't be logged in or if I wouldn't have an account, this would now simply bring me to our sign up page. But as I'm logged on, I can now create a new project, provide some insights, or I can pick one of the projects in my dashboard and start my analysis from this. So in my case, I will now pick this battery cold plate study project that I prepared. I will open it up. And this now opens the project in the browser. So I have here the 3D model of the pack. And what I will be doing now is simply picking the project ID of this project and copy it. And now I will quickly jump over to an IDE for Python. So we can use the API either via Python or C#. In this case, I'm using Python. And what I want to do now is in the project that I showed you, I want to now run all of these different design configurations. So what you can see here is simply that we have here a list of different parameters. So how many holes, what's the diameter, etc. And we will iterate through this list and create models from this. How we will do this is, if I expand here, we will call the API of Onshape, so a 3D CAD tool that is also available via browser, so completely cloud-based. And we will do on the fly, essentially, these modifications and import these models into our project. That's why I will also replace here the project ID and kick off our script already. So we will see then in a second what this does. I take the time in between to show you how this works on Onshape. So I opened now one of these projects on Onshape, and we can see now our cooling plate design. I created in here a couple of parameters. So you see the different numbers and what the current value is. And our API script now runs over these parameters, updates them, and imports these models into SimScale. Yeah, that, for example, define now here this linear pattern. So that's what we are looking at. Great. So we will now jump back to our project. So I can take a look here and maybe we refresh and see if we already got a new model in here. And we can see now I have here the battery pack from version 1 and version 2 that was already in my project, but you can now see that I have here an additional model 1, design iteration 1, and that's now my first model that I can take a look at, and that we will later on simulate then as a convective simulation. So that will now happen over time. So every time I am updating here, I will see that now the meshing also kicked off for this one. And potentially, yeah, we have already the next design that is uploaded. We could have also started this all in parallel, but the upload doesn't take that long. So in this case, we just started it sequentially. So we will leave this script now for some time, let the models all be uploaded to SimScale, and also wait for all of the meshings and simulations to start. While this is happening, so now there was an update of a new model, I will jump over to the same project, but with my prepared result of the validation case. So we leave the API case for now. We will look now at our design validation case. And for that, we want to look at the complete pack. I want to give you a quick introduction to the user interface at that point. What you can see here simply are 3D results of our pack. We see here streamlines. We see the different fields. We can maybe put in the legend here and also show the filters that this is familiar to you. So the post-processing environment might really be familiar if you're using simulation tools already. It's not that different. What is very different, though, is that at all times when you're working in such a project, you can contact us via this chat functionality and you get a response within minutes. So if you are stuck somewhere or if you have troubles, please just reach out to us or make use of this sharing functionality. And then you can not only use the sharing functionality with the SimScale support, but you might also invite a colleague of yours and say, okay, can you look at my project? Maybe you only want him to have view permissions in this case, and you can send out an invite to him if he can maybe help you with it. What you will see is essentially that this person then will pop up here as an avatar on the top, so that you can also see now in this case my younger me popped up, if you can see at the very top, and can take a look at this project and give you some hints on what you might be doing wrong with the setup, for example. That's also what we want to look at right now. So how does such a setup work? Is it complex? Is it simple? So we're just loading now the geometry that was simulated here. I can maybe quickly jump through this again. So if I'm hiding here the cooling plate, we can see the flow region with our inlet and outlet and the different elements. We can see here some thermal pads below this. Oops. And we can see here the different cells and cell holders, etc. So rather a simple pack, but well suited to describe how this can be done and how this is helpful for EV design. How you set up then such a simulation is quite easy. So what you need to do is essentially defining materials. I will not go into details here. I will just show you the different assignments that I did here for example, the aluminum cold plate, the water flow in here, or the battery cells. You provide some boundary conditions, like, for example, the inlet and the pressure outlet here for the top plate, and you provide some additional power sources. So in our case, just for the battery cells, the 2 watt each that is used to heat up our battery pack or dissipate the heat in our battery pack. So that's essentially what you need to do. The rest of the settings is usually pre-filled, that you can also see from these green check marks. So you don't need to touch, for example, initial conditions or mesh settings. You can just use the default settings. But if you want, obviously, for expert users, they are available and you can work with those as well. If now out of our study that is still running, so let me quickly refresh that we can see where we stand with this. So you can see now we kicked off now already multiple meshes and multiple simulations for the model. If we get out of such a simulation in the end an indication of which model might be working best, we potentially want to validate now, is this also really true? So if, for example, we started with a very simple model, so in this case, you can see that the flow channel is quite simple. We might have found out that the a bit more complex flow channel works better. So we now want to run just a simulation replacing these models. What I would do in this case is simply duplicating my simulation, selecting geometry, replacing now the battery with the second version, hitting save. You see now that we can see here this loading indication. It's now mapping all of the assignments that I have for materials, boundary conditions, power sources, but potentially also result controls, etc., making sure that all of our settings stay intact and that I, in the end, only need to now run the simulation again. So if I walk through the materials, you can see still our flow regions are well assigned. We can see the different, hide this, see the different boundary conditions still rightly in place. And what I would do now is simply start off this copy as well. I'll get a little warning here that not all my contacts are completely matching. That's not a problem at all. I'll just start this simulation. And before I really start it, I also get an indication of how long this will take, right? So you can see that we, from the data that we have mainly from our community users, we can give you a good indication of roughly where you will land with such a simulation. So I'll kick this off. And that's also mainly what I wanted to show you for the live demo. And I'll jump back to the slides for a second so that we can wrap up our session. So as a summary, we saw now a couple of colorful pictures that are extremely important if you want to have specifically qualitative information. Do we have recirculation zones, similar patterns? But obviously, it's also important to look at the quantitative data. That's what you can do via the user interface by downloading, for example, the 2D plots, or you can also do this by using the API running in Python and using Python to process the data that you received. In this case, I plotted, for example, the battery cell temperature and its distribution within the full pack. So we can see here we have probably an optimal range somewhere between 15 and 25 degrees. Our max temperature is slightly above that, but the temperature difference looks quite good. So we have 4.44 degrees C between the lowest temperature and the highest temperature. I just plotted here now the random cells ordered from low to high in this case. Or I can take a look at the convective setup that I did. So I can see here I have the different temperatures that I reach on the top surface where the heat is introduced into the cooling channel. And I have the pressure drop for these different models. And ideally, we take now one that works quite well in regards to the temperature distribution, but also in regards to the pressure drop. Great. That's what I wanted to show you. I hope it raised your interest. If so, I can just recommend that you might want to try it yourself. Please also don't be shy. Reach out to us. We're always happy to walk you around or help you discussing your simulation setup. And obviously, I'm very happy if I can now answer some of your questions.